I'm starting the recording. If there were 3 tasks, the first of them ICC, then in order we will do kangaroo and trick. First, ICC, the interactive problem. We are given a tree, or actually a tree is created edge by edge, and for every new edge with some kind of queries, we need to detect that tree. Every query is between this set of vertices versus this set of vertices. We need to check if there is any edge. I muted another person because of the sound. And then they will tell us if there is such an edge or not. Of course, we need to avoid the previous edges. So at any point, our current knowledge about this, about everything, is that there are some connections, let's say from 2 to 8, from 8 to 1, from 3 to 7, and maybe there are alone nodes 4, 5, and 6. There are some connected components here. And how can we find a new edge where we have no idea where this new edge is, maybe here? What can we do? First is we can test every possibility, including maybe some stupid possibilities like this one. Connection between 1 and 2, connection between 1, 4, 1, 5, and so on. If you always check all the n squared edges, and you multiply it by times n, because n minus 1 times you are looking for a new edge, the total time complexity is n cubic, and this should be enough to score 7 points. So 7 points is just what subtask? This one. 15 cities, and then 15 cubic it should be, with some low constant factor. It will fit in 1500. Then what can we do faster here? There's connected components here, and we know that we shouldn't ask queries inside of the same connected component. And also maybe we should ask queries about more than a single pair of nodes at the same time. And for that, first maybe one more subtask, and then I will tell you another problem, something very similar but more well-known. So one more solution here, and it will solve other subtasks, is for every node to check if it is a part of that new edge. Because if there is a hidden new edge, let's say 1, 4, we can of course blindly keep asking 2, 3, 1, 2, 1, 7, and so on, but we just hope to eventually hit that pair, and there are n squared candidates. That's very bad. It would be better to try to find one endpoint of our hidden edge and then another endpoint. So let's focus on that. How can we check if there is a new edge between 1 and something else? Well, we can just ask about set of 1 and everything else. We should ask if there is an edge between 1 and 4, 3, 7, 5, or 6. That's a single query. So like that, we ask set 1 versus set, in this case, 4, 3, 7, 5, 6. Everything except for the connected component that includes 1. If the answer is yes, then we know that this is one of the endpoints. I heard the question. Not. Okay. Then what's
N?
Again, I just heard a single word. You can write in the chat. Now, what is the time complexity, or instead, what is the number of queries? Because that's important, not really the time complexity. As n is small, the limit for the number of queries is much more important than the time limit. So n minus 1 times, we repeat the process of finding a new edge. How do we find a new edge? For every node A from 1 to n, we make a single query. We make a query between A and everything outside of connected component with A. It's easiest to keep connected components with DSU. But if you want to use DFS, it should also be fine. Okay, so what's the number of queries here? N squared. We have n squared queries. so far to find one endpoint. Actually, if the query gives you true, you can just keep searching and then you will find the other endpoint. It doesn't have any disadvantages. So I would suggest something like create an empty list here, and then if query here, if query of A versus everything outside of connected component of A, then here endpoints push A. After that, endpoints is guaranteed to include both the endpoints. And then you're sure about that edge, so you can insert it to the graph with, let's say, DSU. This is still n-squared queries. So let's see what subtask it will solve. Certainly the second one, 50 squared, maybe divided by 2, will be good enough here. For the third one, it doesn't seem so. Maybe with some speed-ups, like not asking unnecessary questions, or maybe what else you could try here is asking questions in random order, but nothing here said in the statement that the interactor is not adaptive. If you have a PDF, it's good always to Control F adaptive, find something like adaptive or malicious. Sometimes they write it explicitly. If they don't say that, then in modern contests, it means that the interactor can be adaptive, because they didn't say otherwise. If the statement says the test is guaranteed to be settled from the very beginning, then you can assume that, otherwise you cannot. And then in big contests like IOI, you shouldn't even ask such a question, because it's not guaranteed. But if it was guaranteed, if test or if interactor is not adaptive, which is not true in this problem, but if it is, then asking in random order, so here reshuffling every time, we can estimate how many queries we need. It's something like that. We have a sequence of n elements. 2 of them are in some way correct, whatever that means, and we randomly ask queries, is this one correct, is this one correct, is this one correct, until we find both correct ones. Then we can imagine that we just reshuffled those, and then on average those two x's are at, let's say, 1/3 and 2/3 of the sequence. That's not really scientifically correct to say that they are on average in those positions, but or maybe I should be more formal about it, but still the following is true. On average, the second hidden thing that you will find among those two in two random positions is at position 2/3 multiplied by n. So if the interactor was not adaptive, then here we would have n-1 multiplied by 2/3 of n on average. Still not enough to solve extra subtasks, so let's ignore this fact. It's useful though in some other problems. And generally, if you have k objects, random positions, then the following is true. The last one is at k divided by k plus 1 times n on average. There is this lemma in math. Similarly, the first one is on average at 1 divided by k plus 1 times n. You can later think about this fact. And obviously it's possible to prove, but it's not important in any way to know the proof. Okay, what else can we do? The second endpoint we can find differently. So here, if we find the first one, so the first such node, again, to check if node is an endpoint, we compare it to everything else outside of this connected component. After we find the first endpoint, so let's say we realize that, yeah, one is one of the endpoints. Now the other endpoint, first of all, needs to be here, so in not the same connected component. Second, there is a way to find it faster. If there is a linear search, then very often we need to try binary search. And indeed, out of k candidates for something, if we want to find the special one that in some way matches one, it is possible with binary search. How? we can write it down as a sequence, in this case 3, 4, 5, 6, 7. They don't need to be sorted actually, so let me mess this up. Still those 5 nodes. And one of them is connected to 1, only one of them. How can I check it with binary search? I can ask if the prefix of them, of half of the sequence, if it's connected to 1. If so, I will get down to this half of the sequence, otherwise to the other half. Or, I know, longer prefix, but let's just say the other half. If you have k candidates, you can ask a query about the first k over 2 of them, and then you will have only k over 2 candidates. So this is the following solution. After the first query succeeds, A compared to everything else, you here binary search A against everything else. By this I mean everything that could be connected to this node A, you can write as a sequence, and there with binary search you will in logarithmic time find that match with A. What's now the number of queries? Well, sadly it's still n squared. It used to be n squared. Now the pessimistic is that it's still n squared, actually n squared plus logarithm here. If something was true about randomness, then this would be much better, because it would be n times half of n plus the first n multiplied by logarithm. So that thing we would improve, this one not really. There are so many subtasks that I'm sure that some of them can be done just thanks to what I've just discussed, but not with only what I discussed. Still a very useful technique what we did here. Then, how can we find the first endpoint faster? How can we avoid asking about every node separately? Well, we can maybe try binary searching for everything from the very beginning. So let me, I will not copy the graph, I will just copy the sequence. There are all the nodes. And now, what's a way to check if 1 through 6 is connected to something else? Sadly, that's impossible, because there might be already an edge between, let's say, 2 and 4. And if you include, actually that's not an issue, but there might be an existing edge between them and the outside world, like that. 4 can be connected to 10 already. So you cannot include 4 in one set and you cannot include 10 in the other set. Otherwise, maybe you would try something like this set versus this one, but we cannot. Okay, what else? Well, if something is a connected component like that, maybe we should treat it as a single node. So not to ask queries that will include such 2 nodes, 1 per set. That's some thought that we can try. What else can be there? Okay, so let's say that there are no connected components yet. So everything is separate. Then is it useful in any way to ask if there is an edge between this half versus that one? Sadly, no, it's not useful. In particular, if we know that there is an edge or we don't know that there is an edge, there is nothing really we can do about it. Maybe what you would want to do is ask something like that. Is there an edge between such 2 sets? Then at least once you know if there is, it's some information. But it's too complicated. Let's get back to our idea of binary searching, and I will tell you how we could find that first edge in logarithmic time. Actually, maybe not with binary search, but with something random. Random, even though we know that the interactive is adaptive. And now finally, let me tell you that other problem that I mentioned earlier. There are actually 2 well-known problems. First one is, given n colored points, find each of them of form xy, find 2 with biggest distance. Now, so first of all, if I erase that word, if I just say given n points, find 2 with biggest distance, there is an algorithm for that. In n log n you can do it by finding convex hull and then doing 2 pointers segment of a convex hull versus opposite segment. There is a way, doesn't matter how. Now if I add colored, find 2 points of different colors with biggest distance, it becomes way more difficult task. So this time I have multiple colors of points, and now we need to find a pair of points with big distance. But this pair is not allowed because both those points are blue. N is around 100,000, let's say. One of the solutions, a very standard solution that we will also use for ICC, is to split the colors into 2 groups. Because, as it turns out, this task is much easier if there are just 2 colors. So the technique that I will show you now is about moving from K types into just 2 types. And it's very general. In this case, if I said that there are only 2 colors, so let's say there can be blue and green, then everything becomes easier, like here, because you can find a convex hull of blue, you can find a convex hull of green, which in this case is, well, just 2 points, and then you can use 2 pointers on both of them. It can be done, at least as far as I remember. But how do we move between, what's the technique? How do we move from K types to 2 types? First of all, we can split randomly. So if we have K colors, you can split the colors into 2 groups. For example, you can say that one group is blue, the other group is yellow and green. Then you treat every group as a new color. Let's say everything here is white, everything there is black. So you color those one color and the blue ones the other color. Then you have 2 colors, you solve the problem, and if the optimal pair was between a point from this group and a point from that group, then you win. So first way of analyzing this is that optimal pair, optimal answer, that pair of points, has probability around half of being detected by this thing. At least I hope so. So if there is some optimal pair, we don't know where it is, then blue color will get to one set, then green color has 50% probability to move to the other set. Hence, this lemma is correct. Now, again, we have K colors. Those colors will split into 2 sets randomly. The sets don't need to be of the same size. For every color you just use rand modulo 2. You have that split. If one of the sets is empty, then just repeat the process. But if they are non-empty, then treat one of this as white, one of that as black, solve the problem for 2 colors, then you have some candidate answer. You might be unlucky. Maybe, in this case, blue and green got to the same set. And then you will find not an optimal answer. That's fine. You have half probability of detecting an optimal pair. So then you just repeat. So the solution to this task, if there are K colors or N colors, I will say K colors maybe, is to repeatedly, like 30 times, apply the random split to 2 sets, and then finding the maximum answer out of everything that we did. And yes, as the question from the chat suggests, we can do this deterministically. Because here, 30 repetitions is all fine, but we can do it instead in exactly logarithm of K. Exactly that much. By splitting according to every bit. So if you have colors, let's say the colors are 0, 1, 2, and 3. Write each of them as a number with binary representation. And then for every position, and let's give it color, let's give it names. Blue, yellow, red, green. For every position, I will split the colors according to their bits 0 and 1. So for this position, set 0 will contain blue and red, set 1 will contain yellow and green. So those are such colors that on this position they have a 0, and then everything else. Then I look at the other position. What's that split? 0 are colors blue and yellow, blue and yellow. 1 are red and green. And it turns out that this is enough. Every pair of colors, at least in one of those two scenarios, that pair of colors is in two different sets. You can check any pair of colors here. Let's say blue and red. Blue and red, we are unlucky here. They are in the same set, but we are lucky here. Blue and red are in two different sets. So we will correctly detect every pair between blue and red we will consider in this scenario. So grab the k colors, let's say numbered from 0 to k minus 1, compute logarithm of k rounded up, so the length of those numbers. For every position, split according to the bit on that position, 0 or 1. You have a split of colors into two sets, create all the points from two different sets, treat them as two colors, and solve the problem for two colors. The time complexity is then log of k multiplied by solution for two colors, whatever that is. Of course, sometimes you can use the fact that multiple times you do the same thing. So in the convex hull problem here, convex hull is n log n because every time we sort points from left to right. But here you can do it as preprocessing. So you can, as preprocessing, sort the points in order to make convex hull faster later. And then log of k times, for two colors, this can be done in linear often time. So that's the time complexity of that colored points problem. And we are done. One more task that you can think about in home is the following. Given a tree with colored nodes, again, n nodes, n is around 100,000, find a pair of nodes with different colors. With max distance between them. So this is, let's say, the title here should say tree colored diameter, meaning you need to find diameter, but the two endpoints cannot be of the same color. The solution is again, or the approach here, you need to multiple times split colors to two different sets and then solve it for two colors. Convex hull for two colors, I believe, is solvable with two pointers, but I'm not 100% sure. Like if you have this and that, you should use here that for one segment here you will know what is the furthest in the other convex hull. Then if you move, again those are two pointers, one pointer in one convex hull, one in the other. If you move, and if you are now here, you will also move this opposite point there, and you will keep moving. And actually for this to work, you need to have a segment in one convex hull, point in the other. So it's not point, it's segment point. For every segment of one convex hull, you want to know the furthest point in the other convex hull, and then also swap those two convex hulls. So for every segment in the blue one, you will need to find the furthest point in the other convex hull. By the way, the source of this problem is the tricolor diameter is algorithmic engagements around 2019 finals. This one, and for that one I don't know. I don't remember where is this problem from. Okay, so that was the technique, and now let's use it to solve the ICC problem. We have our, let's say here 12, the 12 not points. What are we given in ICC? No, I forgot. What are we doing? Oh yeah, nodes. I can, like let's say 30 times repeat, split into two sets randomly. at least if nothing is connected yet. This might be not enough, but on average, this much should be enough, even if interactor is adaptive. So even if interactor is malicious. 2 times log of n times do this, or actually you need to do it as long as necessary. So if it's still ambiguous what should be connected to each other, you will need to keep repeating in some way. But instead of doing this, it's better to use our technique. So just exactly that many times. So for compute log of k, then for every bit position, split according to that position. For example, if you look at the last position, the least significant one, you will just split into even and odd. Right? Your first split will be 1, 3, 5, 7, 9, 11 versus 2, 4, 6, 8, 10, 12. What you're basically doing here when trying such a pair of sets is you will detect if one endpoint is even, the other one is odd. Right? There is a hidden edge, AB. You will check if one of them is even, the other one is odd. Then when the other set that you will check is, let's say, 2, 3, 6, 7, 8, 9, 10, 11 versus 1, 5, 8, 9, 12. Those are such numbers that they have a bit 1 on the second last position. And what you're checking here is your edge between one node where there is 1 on the second last position and one node that is not like that. So you will get information that A is, let's say, this, B is that, and you know that this is 0, this is 1, or the other way around. Like for the last position, it was whether one of them is even and the other one is odd. All right. But that's not enough to know the endpoints, and also some stuff can be connected. So first, let's say, just like here, that some things are already connected. Okay, like this 1 to 8. Then first thing that I do is I find connected components, and let's just call them C1, C2, C3, C4, C5. My task will be first to find connected components that between them there is an edge, and I don't care where exactly for now. So to find every edge, I will use 2 parts, 2 phases. Phase 1, find between which 2 connected components there is an edge. Then, when I deal with those 2, I will use binary search to find a particular edge. To find that, oh, actually it was node number 8 that was connected to node number 4. But first, when we deal with connected components, it's just a sequence from 1 to 5. And then let's try to summarize this and what we do. So, to find a new edge. Step number 1, list down all, let's say, k connected components. Apply the technique of trying every position to make a split. Split of colors or split of connected components. So for example, what we might do is, there will be a split when 1, 3, and 5 are together. That means we will ask a query, is there an edge between 1, 2, 8, 3, 7, 6 and 4, 5? If so, we know that there is an edge between C1, C3, and C5 versus C2, C4. And that's some information for us. Okay, but do we know exactly then what pair of connected components is connected? Well, not exactly. Will we have access to recordings afterwards? Yes, you will. Not exactly. So let's try to understand better what I said here. When doing this check, you will get information if it's even versus odd. Here, if query is yes, it means an edge is between something with position 0 versus 1 on second last position. Here. And here's the final understanding of the technique. Because here's what actually, how you usually call the situation when there is 0 in one number and 1 in the other. We analyze the XOR. So XOR is equal to something, something, 1, something. This is exactly what information we get. Maybe like that. So every query tells us if there is 1 or 0 here. So what we will know, if we look here, after asking those logarithmically many queries, is we will know that XOR of connected components IDs is something. Let's say we say XOR is equal to, say, 7. This is what we know after queries. And then we don't know if this means that maybe connected component number 3 and 4 are connected, or maybe 2 and 5. There are some different possibilities here, but you can handle with that more easily, like with, I guess, binary search. We computed XOR within log k queries. So here what we actually did in this step number 2 is for every position from 0 to log of k, split connected components into 2 groups. If queries equal 1, then the connected component XOR, I apply a 1 there, and then I know XOR of 2 connected components that I need to use something between them. What can I do now? Well, if there are connected components, 1, 2, 3, and so on, and you know the XOR, you have linear number of candidates, and here I would suggest a binary search, and I think even it can be very easy to apply. But how complicated are those pairs? So for example 7, it will be 7 can be like that. What about 6? This is 6 and this is also 6. So is it always true that they have this pattern? Because I wanted to use binary search here. So is it possible that such a pair has the same XOR as this pair? Yes, it should be possible, right? 0, 4, 1, 5. Yep, those two. Those two both have XOR equal to 4. Okay. So I almost said something incorrect. Because now, depending on what we will do exactly, we will either get 100 points or slightly less than that. Oh yes, Sedunion said something nice. We should now analyze it's good to write down possibilities like that. We got the XOR of connected component IDs, and now we know that one of those is something we need. And here we can get rid of repetitions. So always when we have such a pair, then eventually there will be the other pair, right? If we here write down 2, 6, then eventually there will be 6, 2. Then just ignore 6, 2. Only include such pairs that the second element is greater than the first one. This is, say, a vector of pairs. Right? For every number a from 1 to k, the number of connected components, create a pair. This ID, comma, ID XORed with the XOR that you computed. And now, in this, or actually even the list of nodes, you can binary search. So first, let's say that we can binary search like that. Is there an edge already here? If we do it like that, then here's what happens. there is log of k for what we did before, so for that technique, plus then log of k, that's binary searching on connected components. This was, I will say, the technique. Plus, what then? We know two connected components, and we need to find what exactly pair of edges is connected. Like, let's say 1, 3, 7. We know that this connected component is in some way connected to this one. Oh, there shouldn't be cycles. And now I can binary search here, I can binary search here to find which one of those nodes is connected one. So it will be times twice log of n. That's our solution so far. In a moment we will get rid of one logarithm. Right now it's 4 times logarithm, actually smaller than that, because first k is small, later what do I want to say? No, at the beginning n is small, so log of n isn't always fully log of n, and also log of k cannot at the beginning be big. So at the beginning it's big, but at the end it's slightly smaller. What I'm saying is that this log of k sometimes is smaller than full log of n. So all of that, it's limited by 4 times log of the full n, but slightly smaller than that. Let's see how many points we get. For 100, if we just compute logarithm of 100, it is 7. So then 7, oh, and of course we do it n times. We multiply it by n. So it's n log n multiplied by 4. Now if we just compute it, what will we get? 4 times Python. 4 times log of 7, log not defined, so let's just say 7 multiplied by 100, 2800. That's not enough. I believe that actually it's smaller than that, because not always we'll hit a full logarithm, so maybe we would already solve this one. But now let's try to improve what we did, and instead apply one binary search instead of multiple ones. So after the technique, when we have this, I want to get rid of the repeated pairs and then list down all the nodes. Does that make sense? Yeah, because there are no repetitions. So this is a connected component, and actually I can list down that it consists of v1, v2, v3. Then this is another connected component, and I can list down that it has v4, v5, and so on. And there are no repetitions here. This is one connected component, this is the other. So I can just do one big connected binary search on that list of vertices on the left. Asking, for example, is there an edge between this prefix of vertices and everything except for those connected components. So those vertices along with their connected components. Like that, we will find the first vertex. So all of that I want to replace with the following. So I'm not binary searching connected component. Instead, I'm binary searching on this left list of vertices, and then plus another log of n to find the other endpoint. So we now have log k, log n, log n. But I'm sure we can do different things here. I believe that as the second phase, the editorial did binary search on connected components, not on vertices, but well, I'm sure many things are possible. So the summary of this is step 1, the technique, and we then have this. Then after that, for every connected component from 1 to k, if it didn't appear before in any pair, list down its vertices and make this connected component ID XORed with XOR as forbidden, meaning I don't want to list it down later as part of this vector. and just continue that process. I'm now thinking if there are any issues about that. Yeah. Oh, and maybe what's the idea behind what we did? So why is the reason that we need even that XOR? So the thing is, from the very beginning, if we have multiple connected components like that, if I want to binary search on all the vertices or all the connected components, I cannot include even two connected components in the same set. Or in if I include a lot of things and split it in some way between two different sets and then ask a query, I know very little about it. What we know now, thanks to computing XOR, is that maybe connection can only be like that or like that, and no other new connection is possible. So then, if I have 3 nodes in C1 and 4 nodes in C2, I can easily binary search on that list of nodes in C1 and C2, and then ask, is there an edge between those versus everything else? If yes, great, and I can now cut this sequence in half. So ask maybe only about the first 2 nodes, not about all 5. Before computing that XOR, we know nothing about connection and connected
Screen has
components.
max number of users.
Can you repeat?
Yeah, I'm sure.
I again didn't hear that. Cool. ICC is done. There is a small difference here between 5 and 6. So the final 10 points might be difficult to get depending on what you implement. It actually matters if you always hit exactly logarithm of n, or maybe logarithm of only the connected components so far. If you want to see the analysis of the exact number of queries asked, you can read the editorial, and here they analyze if we have the ceiling of binary logarithm of what exactly, and what's the total sum versus what if we improve it a little bit. And then the intended solution apparently asks 1613 queries exactly in the worst case. By the way, if you get 90 points here in such a problem, it might be a good strategic decision to move on to another problem and only later get back here if you have time at the end. Because 10 points is not important compared to the full 100 points. But of course, if you think that you see an improvement and if in a few minutes you can get 10 points, that's a good ratio of points per minute. Cool. Next problem. Next problem is kangaroo. In this one, I will show you some codes too. For kangaroo, there is a sequence of n positions and we need to jump left and right. N is up to 2000 in total. So there are positions. We are given a starting position and a target position, the final position F. And always when we jump to the right, the next jump needs to be to the left. So to the right, to the left, and so on. I think this is a valid sequence. We need to count those sequences, given starting, target node, and size of the sequence n. There are many subtasks. How can we solve them? N factorial. Try all possibilities. Try all the permutations of n values, and for each of them check if we never have 3 increasing values or 3 decreasing values. Easy. Or maybe easy compared to other subtasks. Then, when we make the first step, What now we need to count? What's the remaining state of the game? Well, we no longer have access to that position. Now this is the current starting position, and we have n-1 positions in total. So I would say that what happened here is from state nst, we moved to n-1 remaining nodes. S is somewhere else, so I will call it S prime, and T is also somewhere else. If a moment ago nodes were sorted, or positions were sorted, 1, 2, 3, 4, 5, 6, 7, 8, then after removing one position, they are sorted differently, because it is like that, 3, 4, 5, 6, 7. Position of T decreased by 1. It was 8, now it is 7. So always, if we get rid of a position that was before T, then we decrease T by 1. And this transition we can apply in DP. This is, even if you just read constraints and if you see that there is some process going on in a sequence, you should think about dynamic programming or maybe math. I could believe, after reading the statement, that there is a math formula for the answer, but I'm not aware of any, so we need to use DP. DP of NST, it seems natural to say, well, number of sequences, number of paths from S to T in sequence of length n. But the thing is that we are forbidden from making the same move twice, like 2 times to the right, and after we move from this state here, or from this position we move here, then the next step needs to be to the left. So in this remaining state we have this situation, but also we are forced to make the next move to the left. So I will distinguish 2 possibilities. I will add a dimension for that with info left right. The last dimension means whether we are forced to make a move to the left. If this is 1, let's say it means left. At the beginning both are possible, which just means that the answer is, at the end, the answer that we print should be dp of snt of 0 plus the dp of nst1. Because at the beginning I'm allowed to move either left or right. If there are 10 possibilities like that and 20 the other way, in total that's 30. What are transitions? When you look at the dp of nst, you can, so when looking at this thing, and here's some kind of direction, I would here make a for loop over new position for every I from 1 to n. We consider moving from S to I, and I will be the new starting position. So if I is not T and direction is okay, so if a movement from S to I matches this direction, then I need to update it, and I need to make a transition towards dp of n-1, I possibly -1, not necessarily, then T, again possibly -1, and the new direction, which is opposite to the previous direction. If you moved left, you need to move right next time. The -1 here and -1 there applies applies if S is more to the left. If S is to the left from T, then you decrease S by 1. And that's it. This transition for me, it would be like that, dp of n-1, e-1, and so on, plus equal the current state. So if this was already computed as not the number of paths, wait, what am I doing? No, the other way around, of course. So if I see that for that shorter remaining sequence I have 50 possible paths, I add 50 to the answer there. Time complexity is easy to calculate. It's the number of states, which is also space complexity. So this is n cubic space complexity. And Then transitions are multiplied by n. So you need to multiply it by n and fourth time complexity. And this is enough to get how many points? That many, 36. What can you improve? This is very regular transition. For a long, I got 51. Maybe if the judge is fast and time limit is too big, maybe you will already get 50 points with this time complexity, but certainly you wouldn't get it during a real contest. And fourth is for sure 36 points. Which is, in my opinion, surprisingly many points for this solution so far. Or maybe it's because it's ugly to implement. So I guess that's why it's already a lot of points. Now, improvement to n cubic is easy. We should just see how regular this is. To a long, we here get a summation from a lot of consecutive cells, which almost always with in DP we can do with prefix sums. That is, here we iterate over I, and as long as the direction is okay and I is not t, so for a long range, we will just add up some values from there. Right? For example, if, let's say, S is here, T is there, and I need to move to the right, then possible positions for I are exactly here. And among those positions, I need to add the dp of n minus 1. The new S gets updated as I, t minus 1, and this will say now I need to move left. Where the I minus 1 is in some range. I in range, let's say like that. Where actually L and R are ST, but whatever, or S plus 1 t minus 1. If you want to get the sum of already computed values from a range, very often for that you will use a segment tree, or even easier, prefix sums. So always after, let's say, being done with n minus 1, for all n and for all t and for all directions, for each of them separately, for each triple n, t, and the direction, you need to compute prefix sums over this direction. If this technique isn't obvious to you, I will just tell you a simpler version, simpler problem. You can later solve it as homework, but I will not discuss it in detail. There are n stones in a row, numbered 1 through n. Frog starts at stone 1 and can jump almost k to the right. Count paths from 1 to n. And the constraints are like that. It's a great simple exercise for that prefix sums inside of DP, where n squared DP is easy, and then you need to apply something to very quickly get the sum of a range, or if you implement DP in a different way, you will need to actually add the same value to a range of values in an array. Again, some kind of running sum is possible for that. So that's that simpler exercise if you are not sure what happened here. Now, with prefix sums, we improved to n cubic, and that's enough to get 51 points. If memory was an issue, then we could get rid of the first dimension of DP, but I don't think it was necessary. During a real contest here, a lot of people scored 51 points and nothing more. I believe that actually nobody got 100 points, if I remember correctly. 51 was the max score. And it's surprising because this problem doesn't seem difficult. It's a simple process on a sequence. But indeed, we are limited here by the number of states, and this is just too many states, and we cannot get rid of anything. But all n, s, t are important. Before I move on, before I introduce a faster solution. Tell me if you have any questions so far. If you have a question, you can write it or say it out loud. Also about ICC. I should have asked at the end of ICC, I should have asked if you have questions. Later I will walk you through this code because this is ncubic but different. This problem is very similar to this one in AdCoder. Okay, AdCoder DP contest, so this contest with 26 tasks, has a lot of educational DP problems basically, and yep, this seems to be one of them. I remember that. So this T permutation from AdCoder DP contest is a good one. Thank you for this suggestion. All right, let's try something faster. Usually DP speeds up some process, and we have two possibilities. Go from left to right for a sequence, or we maybe go step by step. So kind of, I would say, the dimension is time. So we consider something moving from left to right, or analyzing a process step by step, and then at every step we want to know what's the current state of the sequence, state of this process, of this game. Sometimes it's different. We can move from smaller ranges to bigger ranges, so that's range DP. It's also possible. I'm sure there are other possibilities too, but those are the main two that we should consider here for Kangaroo. And if you consider step by step, it turns out very difficult to say what else we could improve in the dimension. Right, we have the, after let's say a few steps like that, like what could we know here? What's the state of this game? Well, there are some remaining positions that are still allowed, and well, we are here. We care about where T is, we care about where S is, and it can be any of n positions. Also T can be any of n positions. The direction doesn't matter, it doesn't affect our time complexity. Sequence can be shorter, so it's n-cubic. There's nothing we can do about it. It seems that nothing we can do about it. And from now, there are two possible paths to a solution. Okay, there will be solution number one, and that one is nice, short, left to right. And then, much later, I will describe solution number two, tricky, and it's step by step. Both orders of doing DP are possible here, both in n squared. Let's first discuss this one. And also, this is intended editorial solution. But solution number one, what's that? We want to move left to right, but the steps here don't go left to right. So we will completely ignore doing this step by step. We will instead go left to right. What does it mean? Well, we want to count some kind of paths. And when we look at the first index, the first position, what can we decide about it? Well, it's part of a path, so certainly someone gets here. I will mute IO because there's echo. Someone gets here, and from here we get to somewhere. That's what we know from here. But if you consider those two positions, then eventually it will get very difficult, because after considering the first two positions, already deciding everything about them, you would now need to know the full bit mask of which positions are visited here on the right. That's not good. Again, muting. I think tomorrow I will consider just muting everybody then. Because anyway, meaningful questions are asked in the text chat. We'll see. But a very common thing, especially in counting, very often I saw that in counting, is that we don't care where exactly we will finish. So I will only say that for this first position, it moves somewhere, and also for that second position, it moves somewhere, but I don't know yet where exactly. Okay. I consider the first two positions. For both of them, basically what I decided is that it will be that left turn. Right? Every position, either I got there like that and I move to the left, or instead maybe I move like that and I enter back to the right. Those are two positions. Okay, so for them I decided, actually this is the only possibility for those two first indices. I said something like this happens, and this is already part of that full path. I will tell you one more way of looking at it. So if there are here a lot of things, and I will make some steps. Nope. Done. Then when you draw the full visualization of the final sequence, the technique that we are doing basically means covering part of the drawing. How can I cover it fully? I know how. I will just do it like that. Here you go. If you look only at the first two positions, what do you see? Well, you see that they are connected to somewhere on the right. You don't care about exact connections. You don't know where they go, but they go somewhere. And that's enough. Because there are many ways to finish this drawing. I will decide about it later on. And now for every index, I will have some choices. Either, like here, I start again this kind of turn, or what should happen later, where something else happens here. When I move the drawing to include this position, it will actually finish two edges from the left. So let's see here what can happen for this next index. Either it will again start two new edges, which means that those two will be just extended like that, or possibly it can be the end of those previous ones, but not like that, of course. This is a cycle. We don't want cycles. It can connect green with white. And then the information that we keep is that green one is still going on and the white one is still going on. Now, how can I describe this situation so far? It seems intuitive that I just keep the number of edges that are still going on. So maybe I will use dp of the current position I and the number of active edges that keep going to the right. Except for something at S and T and between of them, this number is actually always even, and I think it's better to look at it as connected components. So I will write it, I will use something almost equivalent, the number of connected components. In this case, 1. But another example of Do I need a longer sequence? I guess so. This is maybe one. This is another. And this is another. If this is the situation on the left, I don't care how exactly they are connected on the left. I only care that there are here 3 connected components. That was supposed to be green. Damn it, colors stopped working, whatever. Okay, now, if I decide for something new to connect 2 old connected components, of course, it cannot be 2 of the same ones, like that. It needs to be 2 different ones. So it seems that we will have something like, if we are here, then the number of ways of expanding, so going to I plus 1, wait, if I combine 2 connected components, so they will be together, I believe that the number of connected components will decrease by 1, right? Maybe, for example, yellow with white will get merged. Then I have 2 remaining, green and the white yellow. And the number of ways of doing it is something like number of connected components choose 2. This is how I multiply, because I choose a pair of connected components. Also, I choose their endpoints, this one or that one. So for each of them, so it seems that we will multiply it by 4. Not really though. For example, when we have green, this guy, then if you look at the drawing that I made, then both endpoints of this green connected component, they are in some way symmetrical. What is the difference between them? Just one of them I drew on the top of the other. It doesn't mean anything. So and generally it turns out that this times 4 is dangerous or actually incorrect because of those connected components that contain only a single node so far, and also because what happens with S and T. So just instead of looking at a drawing like this one, it's much better to say that things are directed. So this is one, this is, let's say, the other. And now if you have a guy like that one, you have a choice of either saying it will be connected with stuff to the right, or it should something, let's say white, should enter into it, and then I will go into, say, blue. And then what's now the number of possibilities? If you have some number of connected components, one of them will go before you, will go before green, and one of them will go after green. So it is actually not CC choose 2, neither that multiplied by 4, it's actually that. Number of possible choices for what goes before green times number of choices out of remaining connected components, what will go after green. Another way to look at it is as follows. You have a sequence. You already made some connections. Let's say like that. And the order is decided here. Then everything like that you can treat already as a string. So this is a string 7 with commas, whatever, 5, 3, 4, 1. And then another one. Let's say there are just a 5. String 5. Maybe also there is 0 for 2, say that 0 exists, whatever. And now when a new guy enters, like 8, it's about merging substrings together. You have a choice of either making 8 a new string, or instead you can do S1 plus 8 plus S2, with new commas, where S1 and S2 are two among those. For example, you can say S1 is this guy, then S2 is this short one. Here you go, that's a new string. So that's a part of the full directed path. This is just part of the path, so a shorter path that goes through stuff on the left there. It is one color, like one connected component, and later when a new guy will come, again we will have a similar choice. Either starts a new string or end an existing one, and also go to an existing one if you can. So like I told you, the definition is something like that. Let's say K or G, like groups. This is number of possible paths on the left from I, or possible, you know, choices, so that we would get number of possible splits into G paths on the left from position I. That's the definition. And then the transitions are first like that. So dp of I plus 1 cc minus 1 plus equal this thing, let's use G, times G minus 1. Also dp of, we can create a new group from the current state ij. I also say this new node can start a completely new group. It's just like that. Easy. And there are also S and T. They are in some way special. So what can happen for S? If there are already some paths like that, for S we have two possibilities. Either S goes to the left or to the right. Depending on what we decide to do with it, a different thing will happen. Let's say that S goes to the left. Then it will go to one of the connected components so far, and now this connected component now only has the open ending. It doesn't have an open start. It has only open ending. Another example, let's say that, so there was something like, I think I need a new drawing. So let's say here. Okay, this is enough. Let's say this guy doesn't exist. Now this is S. If S needs to go to the left, maybe, for example, it will go into the green guy. And now what's the situation when we look at this cut? Where there is a full blue connected component, full yellow connected component, full meaning it still needs to be opened and closed. And then green is incomplete from one side. So it has already a start, and now we need to close it because it wants to end somewhere, which will affect the formulas a little bit. If S went to the left, then those formulas will be different. This doesn't change at all, but this does change. So if I is before S, then we do this. Else, if it's, well, actually, if I in range from S to T, so if S already happened, then I need to know that among the G groups, one of them is actually incomplete. So if I, let's see, it's this, times I decide which one of them should be before and after me. What's that? So now, if a new one needs to be like that, then among everything, including green or excluding green. Let's say that first I want to decide what can enter me. It's everything including green, so there are G possibilities for that. But then if I want to enter something, I don't know if green was already excluded or not, so it's a bad choice. First, bad order. First, let's decide what I want to enter from white to the left. I know that I have exactly G-1 possibilities here, because it's everything except green. And now, one possibility is excluded. Maybe it's blue, maybe it's green, maybe yellow, one of those three. How many people can enter me? Everything except for one that I already used. Now it doesn't matter. Green becomes symmetrical to blue and yellow. So it doesn't matter which one I've just used. Everything else is fine. So I believe that it's G-1 squared. Also here I should say if I is equal to S, then no, something. There are various cases here. You need to figure out what happens before S, after T, between S and T, and exactly at S and T. You also need to consider possibilities S goes left or right. And actually this will imply information like S goes left and parity of N. Actually together, if it is in any way important in your code, it implies whether T goes left, which is not important. Maybe it depends on your code, depends on your approach. But it seems that there are four possibilities for whether S goes left or right and whether T goes left or right. Actually, there are only two possibilities. How you start will affect how you end. So the way I would implement this solution during a contest is I would just from the very beginning say there are two possibilities, whether S goes left or right, and I would twice run a function that solves a problem. Each time I would tell it how S starts and how T ends. Either that or you can introduce new dimensions. But the way I did it, I don't need extra dimensions in DP. This will be everything that I have. No extra dimensions like 0, 1. Okay. Now, the code for this nice solution is in the code forces. Yep, so it's here, Murat. I will give you a link. This is the code. The submission link is unrelated, okay, but this is the code. It's just a few lines of code, and I will give you a link to this comment. So this is nice and short kangaroo solution. You can read his comments, of course, or her. And you can analyze it later for details. I don't guarantee that it will be exactly the same with what I defined. In particular, they seem to look back. I usually call it pull DP versus I prefer push DP. So I prefer using the current DP value to update next values like DP of x plus 1, but those are details. Two other useful, one more extra thing here. For your convenience, it will be much better if you first swap S and F. The order between start and target is not important, so just make start to be on the left from target. And then that's n-squared solution. Still, definition of DP is the same. For a particular position, what's the number of choices so far, so that this would be the number of connected components. Open and close interval trick. Makes sense. Okay, I refer to link in the chat. For the sake of DP, for the sake of YouTube recording, I will put the the important links in the video description. I remember similar task like this one, something about Matryoshka, where if you want to pair up elements, smaller with bigger one, actually you shouldn't immediately pair them up. That's a general thing. So if you have some kind of ordered sequence and you will need to find pairs smaller with bigger, you shouldn't immediately decide about a pair of indices. Instead, just here decide that this one will be paired up with something to the right, but I don't care yet about it. And then the current state is where you are, the position I, and how many ranges are open. Any questions? That was solution number 1 for kangaroo. Solution number 2, and that one actually is explained by the editorial, and it's explained in a very strange way by editorial. I have a different explanation, but at the end the code is the same. Step by step refers to the order in which we consider dp. So I'm actually going to say that there is a sequence, and from the start I make a step and I want to describe what now happens, or at least that's the state of dp. So the definition will be the same. So it's still dp of n, s, t, and direction, but I will not visit all the states. This is how we can get this dp state to work fast enough, because it's right now n cubic, of course. So let's make an observation, and that observation is explained in a very ugly math way in the editorial. I don't recommend that. Instead, I will tell you the following. The following two values of dp are very similar. If I say that this is s and this is t, versus if I say that this is s and still this is t. So in other words, I'm saying that dp of n, s, t and direction is almost the same as that. Why is that the case? Because the paths that work for one s, almost all of them can be shifted a little bit to work for the other s. Let me show what I mean. I think shorter sequence should be enough. By this I mean they are almost the same. I will say this is equal to the same plus epsilon. Okay. So one possibility is, let's say, we go in order 1, 2, 3, 4, 5, 6. Okay, something. And that started here, ended there. Now I want to show a similar path that will start 1 unit before, in a different color, of course, and that will be 1, 2, 3, 4. Oh, no, what do I want to do? Oh yeah, 5 and 6. Done. The only thing I did is I swapped 1 with 5. So maybe more arbitrary drawing. If I have something like that, where this is s, and then it does some stuff, eventually it hits s minus 1 and it continues like that. Instead of it, why did I draw something here from s? That's not really smart. Okay, this was s. Instead of it, I can almost always swap those two elements. Because if from s I go to somewhere on the right, I can always go there from s minus 1. If s minus 1 is connected with two things on the right that are bigger than s, then anyway, it doesn't matter. So if I list down my order, like here, let's write down, say that I had positions maybe in blue. 0, 1, 2, 3, 4, 5. My order of positions in white, the first color, was 2, 4, 0, 5, 1, 3. And then I just swapped those two, 1 and 2. So I said swapping those two is okay. And almost always swapping s with s minus 1 is okay. Because from s, you move right to s plus 1 or bigger. Well, great. From s minus 1, I can also move there. From s minus 1, you move right to, again, s plus 1 or bigger. You cannot possibly move from s minus 1 to s. S was the starting node. What about moving to the left? From s minus 1, you move left to s minus 2 or smaller. Great. Then I could as well move from s. And the last case, from s, you move to, and here, this is the only possible issue. The only case where I cannot swap s minus 1 with s is if from s I move directly to s minus 1. If this is my very first move. So if I start by saying from s move to s minus 1 and then move to the right, I cannot swap them to say from s minus 1 move to s and then to the right. That's the only case. But it's a very limited scenario. So I will say here, and now let's introduce some notation. I will say, let's say inc, it means increasing. So this means what is the number of paths of this length from s to t that first move is increasing, meaning to the right. So increasing means that first direction is to the right. Okay. This is equal to inc of n s minus 1t, except for the case where in this scenario where we start from s minus 1, we first move to the right by 1, because that's something that cannot be replicated here. So from that I need to subtract those cases where from s minus 1 I make a first step to the right by 1. From s minus 1, there is a t somewhere, I move to s first, and then I need to move to the left. Then what's this remaining situation? After I get rid of that index, then those scenarios where I started from s minus 1 and then went through s can be described as the remaining sequence of n minus 1 elements, where the first move needs to go to the left, right? I moved here right first, so the remaining thing is I move to the left. Let's call it dec, like decreasing. Sequence is n minus 1. This position now relatively is s minus 1 because I removed this one. And t also decreases by 1 because I removed something on the left. This is extremely important and basically solves the problem. And why is that? Well, that's okay. I will use that, sure. But if I decrease something here and t changes, then, well, it's still cubic. But t minus 1 decreases along with n minus 1. Those two dimensions together are redundant. S minus 1 you cannot remove. No. Those two. So it. Okay. If what I highlighted was correct, then we could remove s dimension. But this is not correct. We need that subtraction. Or again, if this was correct, then s from the input wouldn't matter. That's obviously not true. It does matter. If you want to first go to the right, then it makes sense that starting from the earlier position, if you start from the very first position, you have more possibilities. So it's intuitive that this expression is bigger than the left one. So we have all of that. But here the observation is that in this expression, t never changes unless n changes by 1. So what I can remove here is I can remove the t dimension. I will move this back, but still with this in mind. The last dimension could be ignored. Before always decreasing n by 1 affects t by 1. Another way of describing it is the following. If I do some stuff here, I change s to s minus 1, possibly removing one position, there is still a fixed number of positions after t. Index t doesn't change if we count it from the right side. the target T will always be on the same position. As long as S is at least 2. So if S is at least 2, then I can apply this. And the number of states that will be triggered by this is n squared. By the way, similarly, if you want to compute decreasing for NST, it will be almost the same as that, with one exception. If you want to start from S and go to the left, so go decreasingly, you cannot make a first step here. So you cannot from S move to S minus 1. So this is bigger, and I need to subtract cases that are forbidden. Among these, cases that I cannot translate to those are where I start from S, I move to S minus 1, and I need to move right. And this turns out to be something like that. I will move it to the right. I'm not describing this in detail because it's very similar to what we did a moment ago. Again, for S at least 2. Assuming that indices are from 1 to n, whatever. So by here I just mean S cannot be the very first thing because this wouldn't work. Now, if S never becomes 1, we solve the problem quickly enough. The last dimension can be removed. T is always in the same distance from the end, so if you know n, you also know T. But why it isn't enough to solve the full problem? Because S eventually will get equal to 1, and then we still need some way of solving the problem. What I did is I said, if I want to count paths that are like that and start from S, then instead I count paths starting from here, and I slightly adjust the result using n minus 1. But never the position of T, if counting from the right, changes. So here I do stuff like that, but eventually I will be here. Now it's a little bit like, I don't know, binomial coefficients. If you say n choose k is equal to n choose k minus 1 plus n minus 1 choose k minus 1. That's great. I mean, for almost any n and k, you say that you apply this formula with some exceptions. You need to decide some base case. For n or k equal to 0 or something like that, you need to say what is n choose k, because you cannot go below. In our case, we need to figure out what happens if n is very small, or just if s is small. So what happens here if s is 1? Question mark. Well, if n is 1, if s is 1, there are two things that we can do. First of all, we can just do the brute force approach. So iterate every I and say that you will make a transition there. This is not that slow, even if you don't apply prefix sums. It's not that slow because there are few states with s equal to 1. If we consider dp of n as t, and also we know that t is redundant, then the number of states where s is equal to 1 is only linear, because only n here can change. So it would be okay if for s equal to 1, we go one by one for all the other positions. But there is an issue with that. If we go anywhere here, that's perfectly fine. If we go outside of t, that's a huge issue because the position of t will change. And we don't want that, because we hoped that this thing will visit only quadratic number of states. ns will be arbitrary, n squared pairs, but t we want always to decrease only if n decreases by 1, so that we could remove dimension with t. But this cannot happen if s exceeds here t, and then they are on two new completely random positions. Now the fix for that is to swap s and t, and not after making that step. Actually, I'm not making that step. I'm not considering those. Instead, I say this. dp of n s equal to 1, let's first a formula. This is roughly equal to, I guess, n, not ts, of course. But let's see a particular example, say 10, 1, 7. Then what I claim is that it's dp of 10, 7, 1, but I would want always the first dimension to be smaller than the second one. So I will use one more symmetricity thing. This is equal to also 10, 4, 10. I mirrored the drawing, left versus right. This is obviously symmetrical. If we have a condition increasing versus decreasing, that it will change here. If we were increasing, now it's decreasing. Also, we swap s with t, so we need to be careful with those things. So it might be not trivial whether now we need to use increasing or decreasing sequence. That, as a reminder, was what is the first move. All right, so we have something like that. And what's the advantage? I will again apply the same thing. So I will keep decreasing s. So this time t is at the end, s is somewhere, and I will use my formula from before to keep decreasing s. And eventually s is position 1, t is position n. And at that point, I can actually iterate everything. So let me write down for, let's say, n is equal to, I don't know, 10. Say that we start from a pair s is 3, t is 6. I will from this, the n possibly will get modified, sure, whatever. I will from this get to s2 t6, s1 t6, or actually that's not good notation, because if n changed, then also t changed. I will say t is 5th from the end. And now at this point I flip, so I say s is, I don't know, something, t is now first from the end, and now I can keep decreasing, something -1 and so on. So here's a lemma that actually talks about time complexity. We'll visit in this full run of dp states where t is at the same position as initial position, meaning the same as how we started, or at the end. Those are the only two possible values for t. Meaning if you started with s being here and t being there, then always we will consider only states where t is third from the end or t is at the end, because you can also get to those states thanks to my flip. And that solves the problem, because we only visit quadratic number of states. I do compute this and that, and it seems cubic, but it's actually quadratic. Only those can be arbitrary from 1 to n, versus t, always for a pair ns, t has only two possible values. So actually this I changed to a dimension 0, 1, where this means whether t is at the end, or maybe t is at its initial position. Initial means same distance from the end as at the very beginning in the input. Transitions are most of the time constant, because I mainly use those two formulas. Clearly constant, right? The only case where I actually iterate with a for loop and transitions are when st are both 1n. So of 1 per state, except for any kind of dp of n, 1n. If I ever hit that, I have linear transitions, but that's okay. The number of such states is very small. And that's the end. This is n squared, memory and time, and ugly implementation, obviously. But this is the intended solution. You can ask me questions if you want, and I will give you some codes later so you can read. First code, n cubic is this is n cubic solution, so it is worth around 50 points, whatever that was, where I define increasing and decreasing, and I use those formulas that I told you. Increasing of nst uses increasing of ns minus 1t minus something, and there is an if for s equal to 1. This is n cubic for now because I hit all the states, I iterate all of them. Then, to improve it to n squared, I made it recursive. So you can see here a recursive function that gets direction, increasing or decreasing, nst. And then, depending on what happens, it uses the formula. Like here, if s is greater than 1, it uses the formula from before. This highlighted thing is the same as the two formulas I told you. It's one of them. And I use a map to memorize, because if you have recursive DP, you need to memorize. I cannot use arrays because the array would have too many dimensions. Array would be n cubic. I only visit some states from the array. So I implemented this thing. I will give you the code, you can analyze it. It is n squared times logarithm from a map, and it's actually too slow. On my computer, this works around 1.5 seconds for a max test. In CSES, it doesn't pass. I don't know if it would pass in the actual contest. I don't think so, because maybe organizers didn't even predict using a map. Now, whoa. If you use an ordered map, it's even slower. And be aware of that. An ordered map is not very often better than a map. Not even in both, if they're random tests or if they're malicious tests, map is generally safer. I use map 90% of the time. So unordered map is not faster. What else can we do here? I tried introducing some dimensions, so simplifying the map. I introduced dimensions, then chose here, said that I have a map from int to int. Then actually, those are dimensions for the direction, n, s, and then I knew that only t will be included in cache. So few things that I would store as dimension in a map, I used outside to be an array of simpler maps. With that, it is memory limit exceeded, because maps have huge overhead. An empty map is like, 100 bytes. It's a lot. So this was memory limit exceeded. I here experimented a little bit, like changed this to short. I combined two dimensions together, stuff like that. But eventually realized that if you have fixed 3 dimensions, inc and s, then I already proved that the last dimension, t, only has 2 possible values. So I changed the map to a naive implementation of a map, which is just a vector of pairs. So this, instead of a map, because I knew that every single map there could be only of size 2, I used a vector of pairs. So every time when I'm looking for something, I just iterate it. I iterate all 2 elements from that vector of pairs. And this passed some more tests. In my computer, this is around half a second for max test, but it's still not enough. And now this version, I'm guessing that would be enough maybe to pass during a real contest, but I don't have any way to check. It should be good enough though. And finally, what I also did is I just created multiple arrays. All my states can be described in various ways. Like there are states where s is 1, t is n, or s is 1, t is anything, or what is here? There is ns, and now one dimension means whether t is at the end or t is at the initial position if counting from the right. and also I have a dimensions for increasing, decreasing. By the way, for those two observation, if S is 1, then consider increasing only. You cannot from S1 go to the left, you cannot go decreasing. And when I did this, it was like milliseconds, it was much faster, and I got accepted. So for this version, especially if you want to do it recursively, which is always slower, you need to do a lot of extra work. This is not a long code, but it was very time consuming to get it right, to make it fast enough. You can later read this code and analyze it. But remember, this was an ugly solution. We don't want that. Much better was to do this DP of IG. There were a few states, and we didn't need to do any like recursive DP because there were normal states. We have a two-dimensional array instead of three-dimensional array is big enough, so I need to use memorization and a map. Time for questions if you have any. Then we move to the last problem. I see that we will go slightly above 2 hours because I wanted to explain multiple solutions for Kangaroo. I think next time I will be more brief. All right, a trick. Where is the statement? No, that's not the statement. Here we are. Numbers from 0 to 2n, and you need to make a mapping from subsets of those numbers to an ordered pair of elements, and there are subtests. I will briefly describe the statement as always at the beginning, and then I will describe only two solutions. So first, how to get the n equal to 6 subtask, 29 points, and then full solution. I don't know solution for other subtasks, only for those two. Okay, first, what's the task? Let's assume for now that n is 6. There are numbers from 0 to 2n. Somebody will choose a hidden number, let's say 3, will split the remaining numbers into two sets of size n each. This shouldn't be 3 then. Now, our program needs, when given a set, to decide what pair of two numbers it wants to print. Say 10, 1. From here, let's say we have 8, 7. The order does matter. And then our program is run again. It gets information, what is n, what are the two pairs, and it needs from this information to figure out what was the excluded element. This is the output of our program. So our program needs to be able to do this, that, and finally this transformation. It's a way more difficult version of a well-known problem, find hidden number, which is given there were numbers 1 through n, one number is removed, find it. So you are given n minus 1 numbers, you need to find what is missing. There are many solutions, but the two main ones are sum up everything and print 1 plus 2 plus 3 plus everything up to n minus the sum that you computed, or XOR everything and print 1 XOR 2 XOR 3 XORed with the XOR that you computed. So you can compute the sum or XOR of everything in the input and then subtract from the sum or XOR of everything. And those are the two ideas that you should consider in this problem. And this time, sum is better than XOR. after we make a proper fix. So if numbers are, how do I do it here? So every AI is in range from 0 to 2n, then suddenly XOR of a lot of numbers can be up to 4 times n. That's a lot, and we don't want to be wasteful. You might argue that sum is even worse. Sum of numbers will be up to n squared multiplied by something. But we don't want the sum of all the numbers, such a huge value. Just like here, we don't really need the full sum. It's enough to know sum modulo n. Or actually, in this case, I want to know sum modulo 2n plus 1. If I tell you digits from 0 to 9, and you want a hidden digit, it's enough to compute the sum modulo 10. So the main idea here is to, from these numbers, the n numbers that are given to us, I want to in some way pass the information about the sum of those numbers modulo 13. So I will take modulo is equal to 2 times n plus 1, which is in this case 13. So I want to now say that this pair, it represents some number from 0 to 12. This pair also represents some number from 0 to 12. In both cases, this is just number that will be the sum of those modulo 13. Then the final program, it will simply, from the mapping that I set, it will figure out, oh, this number, it means the sum of the first set is apparently equal to 11 modulo 13. This means the sum of everything is equal to 6 modulo 13. The total of that is 17. I subtracted from the sum of everything from 0 to 12 and modulo 13. That's the answer. Easy. So what do I need to do? I need to figure out an array, well, 13 by 13. For every pair of numbers, what it will represent. Right? So if f of 2, 6 is 10, it means if the final program gets a pair 2, 6, it assumes that it means the sum of numbers was 10. So the solution to this full problem is basically figuring out a proper 2D array, 2n plus 1 by 2n plus 1. And then final implementation is trivial. For that program that prints the answer, it will just add up those two values, f of this pair, f of the other pair, and subtract from the sum of everything, modulo 13. Deciding that array, though, is difficult. That's the full difficulty. Here's what we want to happen. Whenever we are given a set like this one, when we compute its sum, let's say that sum turns out to be 10 modulo 13. Then there needs to exist a pair here with value fab equal to 10. And usually that will be the case, but we want it to be always the case. So the first program that is run, given a set of numbers, choose a pair, it will check. I wonder if f25 is 10, maybe f26, f27, and so on. Maybe f52, maybe f62, f56, f65, and so on. So there are 6 times 5 possible pairs. If at least for one of them f of ab is 10, then great, we win. If not, we lose. As simple as that. So we need to decide such to the array that for every subset of 6 elements out of numbers 0 to 12, there always exists a proper pair. And what we can try? Well, first we can try a random array and then verify if it's good enough. It doesn't work. It's too bad. Then we can try some function. Like maybe we can try f of ij is I plus 5 times j modulo 13. It doesn't work. There are functions that do work, but it's extremely difficult to come up with one of them. It's much better to fix it, or so to fix an issue if you see something like that. Meaning, so I will first arbitrarily say what every value is. Let's say at random. Again, it's not enough, it doesn't work. But if I see an issue, if I see a wrong subset, I can fix it. I can choose one of the pairs at random, like 6, 8, and I can assign f of 6, 8 is this sum. Maybe this way I will mess up another subset, but that's okay. I will eventually fix it. So we need here a while true function that will just keep fixing stuff. It's not even backtracking. It's just optimizing. I will show you the code now. The code, again, I will share the code with you. Where is that? Ignore that. Ignore this. Okay. So here you can see that I create a function, an array 13 by 13. And it's 6, modulo is 13. This is an array 13 by 13. I create it like that. I have a function that verifies if a mask is satisfied. So I compute the sum of those numbers. Then for every pair of elements in this set, I check if mapping ij is equal to this sum. If so, I return true, otherwise I return false. I will run verify for every subset of size n. Then no. It becomes an optimization problem where you want to improve your mapping. How I do it is I first create a random mapping. I have a function that counts bad submasks, but there are two possibilities here. I'll say, so way number one to implement it is, I think it works, is what I told you before. If you see a bad subset, fix it randomly. Choose a random pair and say that their value is equal to the target sum that is needed. Maybe you will mess up another subset, but maybe eventually this will converge to a good solution. I'm not 100% sure because I didn't implement. But weight number two, and that one is what I implemented, is treat it as an optimization problem. Meaning, I don't even care about solving this perfectly for every subset. I want to make it as good as possible. Meaning that I have a function that tries every mask, checks if checks verified, so checks if it's satisfied, and it counts the number of bad masks. So this function counts for how many subsets of size n I would fail. And I will minimize this value. So what I do in a while true, I choose two random indices, ij, I choose a random value from 0 to mod, I override that value, mapping of ij is this new random value, and I see if a score improves. For now, let's say like that. If this new score is smaller than the previous score, I minimize the number of bad masks, then I replace. And let's see how that works. I started at 188 bad subsets and quickly it got to 0. But here I would say that I got lucky. I will tell you what can be wrong. I will just choose a different seed. Again, I'm stuck. Started from 151 bad subsets, but eventually I'm stuck at one bad subset and nothing happens. Previously it got down to 0, now it does not. I just got unlucky. In optimization problems, and that's very important in Google Hash Code, or what else is there? Reply Code Challenge. In those contests, it's very important to know those techniques. What can we do here? First, I can try multiple times for different seeds, or I can stop this improve function after like million operations and run it again. If I'm stuck, it will start from scratch and maybe then it will succeed. What I did here instead is I changed a single operation here from smaller to smaller than. It's also a common improvement technique. So even if I'm stuck, I will move between similar mappings. This means if the new score is better or the same, apply the change. This way, if I run this again, run this again. I a lot of times have equal values in a row, so I change something even though it doesn't improve the score, but thanks to that, I will not be so stuck. I will change a lot of values, and this way I will faster unlock a possibility of a change down to 0. Almost always in optimization problems, you want to put here if better or equal score, then replace, instead of just if better score. And yep, after we hit 0 there, then I have a proper two-dimensional array mapping that I can use in my program. Then of course I need to implement the something that reads a set and prints the proper pair of numbers, and then something that reads those two pairs of numbers and uses the same values mapping to solve something. I would hard code this array. So here, now that I know what the values here, I would say where is some kind of return 0? Yeah, here. For every I, for every j, print mapping of ij with a comma, then close the one dimension of the array, and let's see what happens. Okay, now copy paste all of that. Paste it, run, and this is that to the array. You don't need to format it better. If I now run it again, why does, oh yeah, I will actually remove create to check. I'm removing the function that initializes everything, and now I've got immediately 0. What I did is called hard coding. I hard coded values in my code. Sometimes then the source code size might limit us, but pasting 100 values is never an issue. Pasting 1 million values would be. 29 points done. Any questions? Okay, then for 100, it's more difficult than that. I need to prepare a table to show you something. I want to change column width. One moment. Where is resize? No, now it unlocks. And now 30. Yeah, good enough. And actually, I will show some stuff here. What we are doing is we are filling an array 13 by 13 or so. So let's say this one. Actually, I will count here 3, 4, 5, 6, 7, 8, 9, 10, 11, 13. Okay, everything else can be erased. Can I delete? Height, sure. Now, values that are on the main diagonal don't matter at all. Also this thing, let's color it. Yeah, nothing here matters. Good. Then I cannot use the main diagonal. Always I need to print a pair. I counted wrong. 4, 5, 6, 7, 8, 9. Sorry about that. Okay, done. So I cannot use those cells. And now this is a 13 by 13 array where I need to, at every cell, write down some value. And some stuff I already know that is stupid, just not optimal, like this. Now, how should I read this array? It means that if there is a pair, let's A is also 1. Can I rename? I cannot, whatever. This is 1, this is 2, 3, and so on, up to 13, let's say. It is not useful to say that mapping of 1, 2 and mapping of 2, 1 is both 7. Because if in my set both 1 and 2 exist and some other elements, I already know that I can say pair 1, 2, let's say it will mean 7, then I want 2, 1 to mean something else. Maybe it will mean 8. Okay? So certainly I don't want it to be symmetrical like that. What else? If somewhere I put, say, 7, it means the following. If those two elements, 1 and 2, both exist, then I will win. So it seems reasonable. Also, it's very important that we have 2 times n plus 1 possible values and n elements in a set. We will use the fact that this is roughly twice bigger than n. Those are not arbitrary values. This, at least for the intended solution, it couldn't be n minus 2 or n plus 2. Or actually, well, it could be n plus 2. It's only easier. But we need n. And how we will do that? Well, if I also put 7 here and there, that's also not good, because I rely too much on this first element. If I want the sum of numbers to be 7, it's dangerous to put a lot of 7s in the same column, because then if I have this number a, or 1, then great, I will create 7 easily. But what if I don't have it? What if I want to create 7, but I need to make it out of remaining numbers? So it's bad to make mappings of the same element, so like mapping of 1, 5, if it's equal to mapping of 1, 6, if it's equal to mapping of 1, 7, let's say all of them are equal to 7, most likely this is not optimal. That's some intuition. Even something like this is not optimal. This means mapping of 2, 1 and mapping of 2, 1, 3, 2, mapping of 4, 5, and so on. So 3, 4, 4, 5, and so on. Still, we rely on similar numbers. I want it to be not correlated with each other. So perfectly, if I here have a 7, another 7 should be far away, like here. So this is one position, this is another, this is another. So maybe mapping of 1, 2 is 7, mapping of 3, 4 is 7, mapping of 5, 6 is 7. I want it to be spread out. So 7, 8. So if I have at least one of those numbers, 1, 2, I win. Or if I want the sum to be 7, and I have at least one of those two numbers, sorry, if I have both. If I have both of these, I win. If I have both of those, I win. And so on. And if I continue this process, 7, 8, mapping of 9, 10, mapping of 11, 12, and let's say mapping of, I know, 0, 1. I need to put 0 with something. If I do it like that, then it's almost correct. It's almost enough. Because let's remember that I have n plus n elements given to me. So out of n elements, it's very likely that there will be a pair 1, 2, or a pair 3, 4, and so on. What's the case when this is not satisfied? It's not satisfied if 1 or 2 doesn't exist, if 3 or 4 doesn't exist, and so on. And this actually, for this pair not to be satisfied, we need to have one of those elements, at most one. Let me give you an example. If we have a set 2, 4, 8, 9, 10, 12, then I win. I got 8 and 10. Sorry, 8 and 9. And sorry, 9 and 10. 9 and 10 are here. I got those two, so I can create sum equal to 7. Let's say that I focus on cases where the sum is 7 indeed. Okay, when do I not win? I do not win if numbers here in a set are spread out like that. So let's say 5, 6, 7, not 8, 10, 12. Here you go. I don't win in this case. But just barely. In particular, if I were given n plus 2 elements in a set, then this already would be enough. Happily for us, our 2D array is very big. It's big enough that we will do this and we will have some extra space left. So let's start. I will now start showing you a solution. If we do it like that, I believe that we could solve the problem, but it will be very irregular, and I'm not sure how to finish the grid. So instead, and I have a drawing here somewhere, I need to redraw it. I want to do it like that. Okay. What are those cells? So maybe I will now, at this point, copy this. Or maybe better, just copy that part. And I will name rows 5, 6, 7, 8, 9, 10. Okay, 10, 11, 12. Done. Okay. So what is this? This means mapping of 12, 1 is 0. Mapping of 11, 12, 2 is 0, and so on. So those elements, great. And those are some disjoint pairs. Right? 12 with 1, 11 with 2, 10 with 3, 9 with 4, 8, 5, 7, 6. I don't want to continue here because that would be redundant. It's the first thing I told you. I don't want my grid to be symmetrical. That would be a waste. If 12, 1 already wins, then I don't want 1, 12 to also win. I want 0 to be included in some way, and also, but before that, let me show you that we have a lot of space saved. We don't, if we repeat this pattern for every element, not just for 0, then we have a lot of space left. So first of all, we have, how many cells do we have? 13 times 12, no diagonals, so we have that many cells. 156 divided by 13 elements, that's 12 per element. So 0 I'm able to write in 12 different cells. And I so far used 6. That's great. So there will be some stuff left. What I'm going to do, by the way, is later put 1 here. And that's, of course, just like always, this is a natural extension, right? Then 2 will be there. Those will be 3s. And so on. There's naturally a lot of stuff will be filled, but the cells that for now are empty and they are still available are those. Every second cell is still empty and available. I didn't use them yet, and I'm free to do so. And yeah, I'm going to do that. And it's easiest for my pairs because I already created pairs 12, 1. So if I have both 12 and 1, I will win if the sum that I need is 0. 11, 2, 10, 3, 9, 4, 8, 5, and 7, 6. By the way, if you're in a hurry or you want to sleep, because it's late. You can also read the editorial for just what this solution does. What I'm focusing on here is more the intuition, or so how we derived it. But if you want the short version, then editorial will tell you what exactly grid we should create. Okay, so now when do I lose? I lose if I have 0 and 1 number from each of those, but it's barely possible. So let me make some fixes. And it's easiest to make some fix around 12, 0 and around, well, 6 and 7. So because I still have a lot of, I can use 12 cells, I can add, let's say 0, 12, maybe 0, 1, or 1, 0, one of those two if it's available, or 12, 0, again if it's available. Let's see if they are or not. This is empty. This I think will be taken. I believe that here we will insert something like 4, 5, 6. I think that here will be 6, so I cannot take this, but that space should be empty. I believe that this is available. So let's say that I will take this 0, 1, and similarly, if we look somewhere here, it should turn out that 12, 0 is available to us. And I will in a moment explain what that gives us. What's the color I need? I need black. Do I have black? No, that's white. Okay, I don't have black, so it will be blue. So there were zeros there. Oh, this is black. No. And I will also use 0 here. And if I remember correctly, there. Visually, it doesn't matter that much, other than thanks to visualization, we see that those cells are indeed available. But now, here's what kind of logic I will want to use. I will want to use pigeonhole principle, but it's very, very easy version, where I will want to say this. If I look at this triple, 0, 1, 12, if I have at least 2 elements among 0, 1, 12, I win. If I have at least 2 elements among 11 and 2, I win. And so on. Let me rewrite it. I lose if I have at most, so to force me to lose, we need to exclude, give me at most one element among that. Force me to lose. Give me at most this. Give me at most (11, 12), and so on. And repeat that for all those pairs. And I want to say that you will need to, in total, give me fewer elements than 6. This is not yet true. Let me finish this, so we would actually verify how much better we need to get. Those are pairs 10, 3, 9, 4, 8, 5, and 7, 6. So you need to give me at most 6 elements. Wait, what does it mean? That's suspicious. Meaning you cannot give me, but yeah, that's fine. So those elements in total cover everything. And those are disjoint sets. In total, give me at most 6 elements. This is how that sums up to. And what I proved is the following then. If I was given a set of 7 elements, I would already win, because this would be contradiction. To make me lose, you need to give me at most 6 elements. At 6 elements, barely, but still, I'm able to lose. So, but here losing set is, for example, 1, 2, 3, 4, 5, 6. This is one from each of those, and barely I'm not able to do anything. There is no pair here among those, just barely. But still I have so much empty space here, and there are various ways to fix it. Looking at just this, you could say that I could add pairs like I don't know, let's look at those two pairs, 11, 2, 10, 3. If I add all those pairs, like 11, 3, 11, 10, 2, 3, and 2, 10, if I add all of those, then also if you give me one element from here and one element from here, I will win. And then it would be enough. So if I'm able to say that mapping for all those pairs is 0, and then corresponding shifted mapping I will apply for 1, for 2, and so on, I will win. Sadly, this particular quadruple will not work, because if you keep shifting it from 0 to 1, 2, 3, and so on, you will fail. But something similar will work. And just like here I did something for 0, 1, and 12, I will do it nearby 6, 7, maybe combined with 10. And I'm not sure if I want to visualize it or write it down. So maybe, not to make a mistake, I will look up the pairs that they write in the editorial. Trick. Okay, so there are those pairs and they are listed here. So let me mark them. So where does 0 appear so that it would work? 0 to n. Oh, apparently they do it in the same two positions. So I will just write that because I'm sure that it works. There is 2n, 1 and so on, and then 0 to n. I thought that that's taken. Let's see. Yes, it's empty, just like those green. Okay, so 0 to n. I'm just rewriting highlighted stuff. 0, 1, n, 2, n, 2, n minus 1, n, 2, n minus 1, 4, n plus 1, and 2n minus 3. 2n minus 3 is here, comma, n plus 1. There. Okay, those. And this is the solution. So zeros need to be in those 6 positions that we already marked. Those, I will repeat them in blue. And those few scattered around positions. They are not extremely random. First of all, they are all in green places. At least I hope that they are. I'm not sure what happened here. Maybe I just shifted it by 1 in some direction. Yeah, so something is wrong by a little bit. But it doesn't matter too much how it looks like. You need to choose them among green spots. So I believe this one is wrong. Everything else seems fine. Like, yeah, like this one is fine. It's between 1 and 2. And the idea is that we slightly improve this situation. What will happen is that then, so a moment ago I showed you that if among triple like that, you will list down all the pairs. So you will say mapping of 0, 1 is 0, mapping of 0, 12 is 0, mapping of 1, 0 is 0. If you do all of that, then if you have at least 2 out of those 3 elements, you will win. Then what happened here in the intended solution is that we also applied the same logic for other triples. Those triples are, I don't know, what triple do they have? Like 4n plus 1 to n minus 3. 4, n plus 1, 2, n minus 3. Apparently this worked. So in our case, 4, 7, 2, n minus 3, 9. So they did something like this. The order doesn't matter too much. Well, maybe it was mapping of 4, 7. Of 7, 9 is 0, and let's say mapping of 4, 9 is 0. Could be mapping of 9, 4. At least one of them is required. And if this is true, then if you have two of those three elements, you will win. So now the idea is that if you have those 2n plus 1 elements, which is in our case 13, okay, so we have 13 elements, you need to create, I showed you before, 1 triple plus 5 pairs. It was here. This wasn't enough, but if you create 3 triples, that's 9, plus 2 pairs, this will be enough. So you need to choose 3 triples of indices, make for all of them, for all pairs between them, mappings equal to your desired sum, like 0. Then for 2 remaining pairs, also just make a single connection. I will give you a bigger example. Let's say that we have 21 elements. Then I will choose 3 triples, and 3 triples that takes 9 elements, 21 minus 9, 12, so 6 pairs. Right here. Like that. So for example, this could mean that I choose triples 0, 1, 2, 3, 4, 5, 6, 7, 8, and also pairs. Let's say 9, 10, 11, 12, and so on up to 20, 21. I messed something up, 19, 20. Okay, and I say mapping of 0, 1 is 0. Mapping of 1, 2 is 0. Mapping of 0, 2 is 0. 3, 4, 0. 4, 5, 5, 3. Okay, again, for 3 pairs among these, then for this single pair, for this pair, and so on. Once you do all of that, you will win if you have 2 elements from one object. But the thing is that now pigeonhole principle will tell you that you have enough elements. Because the number of objects here, there are 9 objects, n minus 1 in general, or before I showed you 5 objects. For n equal to 10, I showed you how from 21 elements, split them into 9 groups, triples and pairs. Then pigeonhole principle and just the logic tells you 10 elements and 9 groups. In one group there will be 2 objects, so you win. The thing is that to choose those 3 triples and their remaining pairs, it cannot be that easy, because then by shifting by 1 it wouldn't work. So it needs to be slightly more chaotic. So to show you now, these are the final few minutes of the analysis, by the way. To show you now what will really happen, so I will also insert 0 in some few extra positions. I don't know which ones exactly, let's say those. And then I will apply the same for 1, everything shifted by 1, to down and right. So there was 0 here, there will be 0, 1 there. 0 here, 1 there. 0 here, 1 there. I don't know. And I think they told us to put 0 here or something like that, so also there. Done. Then the same for 2s. This one copies there. There is 0, 1, 2, 1, 2, 2, 1, 2. Makes sense. 2. This is not 1. This is messed up. Maybe okay? No, everything is okay. And so on. Or you can just think about it this way. If there is a 2 here, then 3, 4, 5, 6, 7, 8. 3, 4, 5, 6, 7, 8, 9, 10, and so on. 3, 4, 5, 6, 7, and so on. Is this an issue? Yeah, this is an issue. No, nothing could be here. But yeah, so in blue nothing was there, so I shouldn't have written anything there. Three, 4, 5, 6, 7. And I think you get the idea. 5. And again, I did something wrong because 5 now would trigger here 6, but apparently I started wrong. Yeah, I'm not sure about that. Anyway, this choice that we start with, it needs to satisfy that we need to be able to continue like that. Move by 1 down and by 1 to the right, write the next element there. So if 0 is here, then 1 is here, and so on. In other words, it just means that however you start, so let's leave only zeros. Every diagonal needs to be taken at most once. Okay, so if you start with zeros, this 0 takes the whole diagonal with it. Okay, this is the whole diagonal taken by 0, and nothing else can be taken. What is after that? This. Okay, and there cannot be any collisions with that. This 0 means that the whole diagonal, this cell, this cell, this cell, and so on is taken. As long as you satisfy that, you're okay. And yeah, that's everything. For the exact coordinates, the editorial is best place, and the coordinates are listed here. You can use them. But I think it's more beneficial to actually come up with them. But from what I told you, that should be enough for you to figure out coordinates yourself. And again, we use all of that to make 3 triples, and the remaining elements split in pairs. So if there is like here a pair, let's say 10,5, you don't want to use 10 and 5 anywhere else. You maybe want to use also 11, 4, and some other triple of positions. Like you might want maybe some kind of 7, 4, 4, 10, and 7, 10. It doesn't matter if you use 10, 7 or 7, 10. Both will work. If you explicitly make a 2D grid, then it will be n squared, the time complexity. But of course, you can just do it with a formula. And here I have even a code for that because I tested what they said in the editorial. And this is the f function. So basically, this function is a solution. I just used formulas for that. Given a pair of coordinates ij, this function returns what value should be written there in a grid. And not all cells we use. We actually here use at least 50% of the grid, but not the whole grid. And eventually here I could return anything. 5, 4 would be okay, 0 would be okay, whatever. So you can as well analyze this code and match it with the editorial. And yeah, so once we have this, the program that gets a pair of numbers and prints the solution is trivial. If you are given a set and you want to find which pair of elements gives you the proper mapping, then I think that trying at random might be okay, but if not, then you need to reverse this function. Like it will be like given a difference. If you want mapping of aj is equal to, let's say, 7, you want to quickly find what pairs ij will give you 7, but this grid is very regular. If I told you here to look for number 5, like number 5 will most of the time will just take this this diagonal, just shift it down and right by 5. So 1, 2, 3, 4, 5. 5 will be here, there, and in a few other places in the grid. So it's not difficult to also reverse, to say, given the target value, where is it in the grid? And it's in linear number of places. So given a target, you will check linear places for whether this pair of numbers are both in your set. And done. That's 100 points. Questions? I will in a moment say some organizational stuff. When you explained ICC, you mentioned the longest distance between two different colored nodes in a tree. Do you have a link where we could submit? No, it's a private judge, so I don't have any link. You would need to test it yourself, so implement a brute force with DFS and just try random trees. Sorry about that. The convex hull task with colors, I recall, is from CodeChef. Maybe it will help you find it. Okay, then we are done with analysis. So last thing is the so what happens next? As I told you, so Monday today was 2016 day 1. Tuesday will be CEOI 2022 day 1, so the real contest. It's in Codeforces. I mean, in Codeforces at least it's announced. CF block. I will make a short analysis for you after the contest, but I will likely not be able to solve all the problems, at least not in detail. So expect a shorter thing. I'm planning also a lecture tomorrow, but that also depends on the time. I think COI mirror is later than our classes today, and a lot of you couldn't attend, so I will see about that. Then on Wednesday we continue the COI 2016 day 2. Sorry about the technical issues today at the beginning. So the statement in CSES incorrectly said that you need to read input output, while I mean they mentioned files. You actually needed to read from input right to output. I'm sorry about that. And about files for the interactive problem, I'm sure that a lot of you wasted a lot of time. But Wednesday I think will be the same style, also CSES, so now everything should be clear. And very important, every one of you needs to register for that Huawei survey. So Huawei is sponsor of this camp, even though it's a very small, unofficial camp. Still, we have a sponsor, Huawei. This is why it's all free for you. And you need to register there. You need to fill the survey, which will take you a few minutes, so whatever. But also the emails from that survey we will use for the leaderboard. So the leaderboard will be Google spreadsheet, just like this one, where you will be invited to that spreadsheet by emails that you provide in Huawei survey. If you don't have Gmail account, then as an exception, you will communicate with admins in Discord another way to say what your scores were, so we could create a combined leaderboard for this camp. The leaderboard isn't that important, it's for your convenience. The survey actually is obligatory. If somebody doesn't fill the survey by tomorrow, you will be temporarily kicked out of the camp. You can rejoin once you fill the survey. I will also write this down in Discord in announcements, and yeah, please fill it perfectly. Just do it in the next few hours. If you have any questions to me, of course, general channel is also fine for that. I will upload the video recording from today to YouTube. First, it will be private/unlisted, so I will give you a link. At the end of the camp, I will also publish the link in Codeforces. But for now, treat that link as something private just for you, participants of the camp. And that video link will also come with my codes. I will insert them and put everything in announcements. Good. Then hope you like the contest, which was a difficult one, I believe. I encourage you to absolve as much stuff as you can. Written editorials you will find in the internet. They are not perfect, but hey, it's something. And I will try to help you a little bit with absolving, but I'm not able to help you with codes. So if you have questions about the logic of something, if you didn't understand something in the editorial, I will help you. If something doesn't work in your code, I will not help you. I'm not able to. There are too many of you. Then just use stress testing, kind of compare your answers with somebody else. Replace part of your program with a brute force, check if it works, stuff like that. Okay, that's everything for today. Have a good evening, everybody, or a good night, and see you all tomorrow. Bye.